Okay, welcome everyone. Today we are lucky to have Igor Pak telling us about combinatorial inequalities and combinatorial interpretations. This is the first part of the 3 lectures. And tomorrow we'll meet in Open Hall, same time, and the day after tomorrow we'll meet in Smart.
Thank you. Thank you so much, Pami, and thank you for having me. It's an honor to be here and be speaking to you. So I'm going to give a Blackboard talk, and I feel sort of bad for people all the way in that corner, but maybe you actually don't want to see what I'm writing. So sort of enjoy the ambience. I don't know. So because I do have the luxury of giving 3 lectures, the first lecture is going to be truly introductory and sort of like. I'm going to give a lot of examples, and I'm not going to dwell on too much. And if I don't feel, I've prepared a lot of examples, and if I don't give some of them, that's okay. So feel free to interrupt me, ask anything you want. Today is all good. Everyone okay with this? Somebody say yes.
Yes.
Okay, great. So I'm going to talk about combinatorial inequalities and combinatorial interpretation. And today I want to sort of write combinatorial interpretation. Sorry. So what I want to do is give a whole bunch of combinatorial interpretation and sort of explain why we're doing what we do, what's going on. Because that is a rather strange idea, and if you're a combinatorialist, you don't think it's strange. But if you're not a combinatorialist, you might think it's like a strange idea. So suppose essentially we have a combinatorial. So essentially we're looking for combinatorial interpretation of numbers. Okay, that's already strange because usually people already have a lot of combinatorial objects and they want to count them. So in some sense, it's an inverse problem. Okay, and inverse problems tend to be hard. So there are 2 sort of sources of combinatorial interpretation. So suppose you have an equality. Suppose you already know there is an equality A greater or equal to B, and you want to find the combinatorial interpretation of A minus B. That is the first typical thing you ask. And obviously, if those are just numbers, you can do whatever you want with them. You can have lots of potatoes with that number. But that's not so when I'm going to say combinatorial interpretation, I'm actually going to mean something. And but before I do that, there is another source of. I'm not going to talk about too much about that, but I'll start with that. So suppose you also similarly, if you have an integer which divides A, you might also want to find the combinatorial interpretation for the ratio. Okay, and those are somewhat distinct problems, but they're also somewhat connected to each other. And I'll start with that because that is a little bit easier to start with. So let me see how. Let me keep writing about. So let's sort of take example. So let's do it. Let's start with examples. And example 0 is going to be little examples. So it's pretty easy to see that k factorial times n minus k factorial divides n factorial. And the reason why it's easy to see is because n factorial divided by k factorial n minus k factorial, we usually denote this by n choose k. This is what we start with in combinatorics. That's number of k subsets of an n set. Okay. I'm not going to ask if you know that. But it does tell you something interesting. It might take some effort to figure out that this number divides up. So this you can say that this is a weakness of the fact. Okay? So I would call this example kind of trivial. let's go with a somewhat more complicated example. So it just so happens that 5 divides 5n minus 1, p of 5n minus 1, where p of n is number of lambda partitions of n, where partition is the sequence lambda 1 greater or equal to lambda 2 dot 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 greater or equal to lambda L, and the sum of lambda I is n. That's what I mean by partition of n. Okay. Now, once you write that, that's not obvious at all. That's a theorem. That's one of the Ramanujan's congruences. So let me write here. Ramanujan's congruence. And but once you write it like that, you want to know what's the combinatorial interpretation for the ratio. And there's a theorem to that effect. So this is a theorem by Dyson from well, it's not really a theorem by Dyson, but I don't want to write Atkins, Winnet, and Dyer's names. It's a little longer. So I'm going to write it like this: 1/5 of p of 1/5 of p of 5n minus 1 is equal to pi of 5n minus 1 for every I, and where pi of n is the number of partitions, lambda partition of n, such that lambda 1 minus L of lambda is equal to I mod 5. Okay. So there are a lot of things written here. Let me let me write here for one I between 0 and 4. So I'm saying that this number is an integer. It's equal to number of partitions. It's sort of easier to draw a partition that way. And we're taking the first row, that's lambda 1. We're taking the first column, that's L of lambda. We're subtracting one from another, taking that mod 5. Now the set of partitions, P of 5n minus 1, this set of partitions is divided into 5 equal sized buckets. Okay, so those of you who know what was happening in 44, basically Dyson was sitting in his Cambridge dorms without lights and without anything, and he was bored, and he came up with this statistics he called rank. Now we call it Dyson's rank. And he couldn't prove it, but eventually Atkins, Winnet, and Dyer proved it. Okay, now if you think about it, it's a remarkable result. However, it sort of goes against combinatorics tradition in the sense that the proof of that result is actually much harder than the proof of this result. And typically, when you're looking for combinatorial interpretation, you actually want it to be helpful. So you want the proof to tell you something. Okay, so that's not like that at all. So that's a much harder result. Is everyone okay with this?
Is there something similar for other integers besides 5?
So the original congruents were also 7 and 11. Is that what you mean? And yeah. So for 7 it works exactly like that, and Dyson also conjecture that. For 11 it doesn't work at all. And eventually, and this whole story is super famous in the area. So eventually, Andrews and Garvin figured out the common statistics which divides all of them into equal buckets. But it won't work for like products of a bunch of 5s and 7s, which is also part of the Ramanujan's congruences. And then things become more complicated. Everyone okay with this? Okay, so I would call this easy. So example 2. So this is going to be the hard one, and so there is a theorem with slightly unclear naming, so I'll call it Smith thought. And it's also from about 46, which says the following. Suppose G, VE, so this is a 3 regular graph. Okay, this is a 3 regular graph. So it's sort of locally looks like that, and I'm not done. Okay, so then number of Hamiltonian cycles in G is even. That's what they prove. And by that, I mean Todd wrote the paper. What Smith did, nobody knows. Okay, so Todd's proof is a double counting argument. It doesn't actually tell you how to divide this thing into 2 parts. Just like Ramanujan's original proof is based on identity. It doesn't tell you how to divide the set of partitions. So now one can ask a question, and that's a hard question. So, so what does that count? Does it count anything at all? You see what I mean?
What's a Hamiltonian cycle?
Oh, good question. Hamiltonian cycle is, let me see if there is one here. I don't know actually. So Hamiltonian cycle is the one that contains all the vertices. Oh yeah. Okay. Everyone good with this? All right. And I don't know. I don't have an answer to that question. But I have a basic understanding that the answer is going to be no, in a sense that under conditions of some conjectures, I'll explain more later. This is probably not going to work. You're not going to be able to say, yes, 1/2 of the number of Hamiltonian cycle is this nice set of combinatorial objects, or there is no way to divide Hamiltonian cycle into 2 nice buckets for which are going to happen to be equal for some complicated reasons. So just like here, it's actually pretty hard to prove that P0 is equal to P1. It's very easy to prove that P1 is equal to P minus 1 or P4 by doing conjugation. But it's going to be hard to prove that the respective set of partitions have equal size. This statement tells you much more about what's happening here. It's a negative statement about this. Everyone okay about this? Okay, good. Yeah, you sure? I feel like there should be more questions. Okay, maybe that's too easy. Okay.
Exactly, you know, loops or?
No. It's a simple theoretical graph. All right. So now I want to come back to inequalities. So from this point on, I'm going to talk about inequalities, and I'm going to start with one inequality. So from this point on, I'm going to teach you stuff that most of you know, and it's going to be great because then I can go very fast. But most of you doesn't mean all of you. Okay, so some of you will know different stuff. So here's something that all of you will know. I'm gonna concentrate on the inequality n choose 0 less or equal to n choose 1 less or equal than n choose 2 ... It doesn't go all the way to the end. It ends with n choose n over 2. Okay. So there are many proofs of that inequality, and proof 0 is a trivial proof. You use that formula over there, do a substitution, you get it done. Okay. I asked some historians, and apparently this inequality goes back to 13th century in the rabbinical literature. People looked into that. They did not use that that way to do it because that wasn't known. And they didn't prove it, obviously, but they observed it. It was known for a while. People used to title sections of manuscript with different subsets. Don't ask me why. So here is a the kind of proof that people in combinatorics usually do, and the kind of proof is basically the following. So I'm going to do it. So I'm going to do an injection, and the way injection works is I'm going to try to draw this as best as I can. Well, I'll try to, let me still do this. So I'm going to get. So how about this? So essentially, I'm gonna interpret a binomial coefficient as what we call at the lattice path, yeah, from 0, 0 to whatever it is. And now what I'm gonna do is I'm gonna draw a line which is gonna be so one level above the endpoint here, and I'm gonna reflect. So when I reflect, I get something something like that, basically. That's what we get, and that gives you an injection from one set of lattice paths counted by binomial coefficient to another. This is called reflection principle. And this is a typical proof we give to undergraduates, or at least I do. So one important thing is this is not a injection, so it's a combinatorial proof of the fact that n choose k minus k less or equals than n choose k.
I missed something. What does the picture show?
So paths which go to here are counted by smaller binomial coefficient. Paths which go there are counted by a larger binomial coefficient.
So the endpoint is n, and then k is the number of times you go up? Is that
So you go up k times down n minus k times.
Okay, and then.
And to that one, and to this one, k minus 1 up and minus k plus 1 times down. I thought you knew that. I assumed that everyone knows it. Okay.
Exposed.
Okay, this is, well, then maybe I should tell you who came up with this thing. So this is, so the wrong attribution, I'm just going to give you a wrong attribution. This is by André in 1887. Somebody figured out that he did something else, but in French, which is why most people attribute it to him. So the whole thing is viewed in the context of the ballot problem as an, so I may as well tell you this at the end. So basically n choose k minus n choose k minus 1 is equal to number of, well, I'll write it this way, 0, 1 sequences with k with k zeros n minus k ones and such that number of zeros in every prefix is less or equal than well, I'm sort of doing it wrong. Well, I want to switch those. Number of ones in every prefix is less or equal than number of zeros. I kind of like that better. So zeros come first. So in that, so this result that the number of those sequences is equal to difference of binomial coefficients. That is called ballot problem. That was solved by Bernard. That was solved by. Let's see. Bertrand, also in 1887, and Andre on this result. So now once I write it that way, this is a clear combinatorial interpretation for the difference. You don't need more. But you might still like more proofs. So I'm going to keep giving you more proofs just so you can see the difference. Everyone okay with this?
Could you explain how
Yes.
you get the relation with those?
Yes.
And-
So I think of
and
so I draw this red
No,
line.
no, just that you get the binomial coefficient. I didn't understand what you.
Oh, okay.
counting.
So when you're starting at one point, you're going to another point. The number of such paths is going to be a binomial coefficient. So more traditional picture would be that if you have k here and minus k here, and you're going. So this is the same picture, just tilted. Okay. But when you tilt it, it's easier to think of reflection. Any other questions? I want to give you two more proofs.
And should we see that from this picture, or are these different principles different?
No. This follows immediately from here. And that's because you're asking yourself, what is not being cancelled under this involution? The only thing that's not being cancelled are those things which never cross the red line to begin with. And if you interpret what, those sequences as going up at zero, or whatever, going, you have to be a little careful. Going up is zero, going down is one. Then you get exactly that. That's not a mystery at all. Question? No. Go ahead.
I'm sorry. Do you reflect at the first crossing or the last crossing?
I reflect the first here. That's why I drew it. so I go one step up from the bottom. I reflect the first crossing, so that when you undo it, there is a clear way to do it. Good, thank you. So I want to give you two more proofs. Which is all embarrassing. You understand, right? That it's sort of weird to give multiple proofs of the most trivial identity you can see. But there's a point to that. The point is different proofs lead you to completely different studies. So the next proof is going to be linear algebra, which I like to abbreviate as LA. So I'm gonna take denote by lambda n the exterior algebra. So this is xi xj equal to minus xj xi for all ij, and so lambda n is going to be graded. Yeah, and dimension of the graded component. Again, I'm assuming that you've seen this. That's a binomial coefficient in just k. And now it's sort of sometimes it's easier to prove this kind of result when you have a nice map between spaces rather than when you have a injection between objects. So one can consider a map. Let's call it slightly suggestively delta. So f is going to go into f times c1 plus dot 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 plus cn. Okay, and now you can. This is the most simplest thing you can think of, and now you can figure out why is that, and why there's no kernel when k is less or equals than n over 2. And let me not write more than that. So once you do figure out this proof by itself leads you to wonders of the world. That eventually is what led to, I don't know how much I want to say, but this is the heart of the idea of using hard lectures and everything else that follows. Okay, in this very, very basic proof. And but I do want to give you another proof. So notice that those proofs are very, very different. Okay. And this proof cannot be converted into that without doing anything.
You call this combinatorial interpretation or
No, not at all. No. This is a combinatorial interpretation. This is like an algebraic nonsense. Okay, which doesn't mean that it's not useful to proving results. it's extremely useful, as you can hear from other people telling you stories. But I'm just not going to tell those stories. So I'll give you the third proof. The third proof is analytic, and I'm gonna define. So suppose x1 dot xn are non-negative integers. Sorry, reals, and I'm gonna write something. I'm gonna write 1 plus xit, product of I from 1 up to n. This is gonna be sum of elementary, well, I'll write it ek, elementary symmetric polynomials. So k from 0 to n. Everyone okay with this? Elementary symmetric polynomial. And so here is a theorem that according to my very shallow historical research due to Newton from 1707. Ek, I'll just write ek. It's going to be ek of all of x1 up to xk, ek over n choose k square greater or equal than ek minus 1 over n choose k minus 1 times ek plus 1 over n choose k plus 1.
It's for everything.
Yeah, for every k. Well, whenever it makes sense. And so now it might take a minute to understand that this is a much stronger result than this result. So let me take that minute and explain that. First of all, one should deal with log concavity notions. So if you have, so let me write it this way: a1 less or equal to a2 dot 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 less or equal to am greater or equal to dot 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 up to an. This is unimodality. Okay. So if a sequence satisfies those properties, that's unimodal. If it satisfies the property ak squared greater or equal to ak minus 1, ak plus 1 for every k, that's log concave. And if it satisfies further ak over n choose k, and then basically if it's log concave for those, then this is called ultra log concave. Ultra log concave. Okay, so those, so each of the one lower is stronger than property above. This one is trivial, this one almost trivial if all the numbers are positive. Okay, so now what this is saying is, in particular, this is saying that ek square greater or equal, ek, basically ek is unimodal. Yeah, it's a stronger result. If ek is unimodal, now take all xi's equal to 1. If all xi's are equal to 1, those are binomial coefficient. There's nothing else to say. And that proof, even though it's historically much older than that, also led to flurry of activity about people talking about real rootedness and so forth. And that's where various notions of positive and negative dependence came from. So different proofs, trivial ones, several non-trivial ones, lead to different stuff.
What was Newton proving this?
What?
Oh, what the ingredient of Newton's?
Oh, he defined derivatives a few years earlier. And he used that. The proof is one paragraph. This is nothing. I'll keep it as an exercise, even though if I had like 10 lectures, I would prove it. This is not a hard exercise.
Same question, you call this combinatorial or not?
Not at all. Not at all. This is some analytic nonsense. This is the same answer, just a different words. Yeah. Good point, and good thing. I expect other people other than Avi also to nitpick things I say. So essentially, we want those kind of proofs, okay? And that's and if you go through the literature, you understand that all proofs and combinatorics, you start wondering why some results, some inequalities do have combinatorial proof and some don't. Okay, and before I define everything, let me prove, I actually want to prove one non-trivial result. It's a very well-known result, but still non-trivial. Okay. So I don't know at what number I am. Let's say 4. So suppose G is a PE. That's a simple graph. So no loops, no multiple edges, even though that's not super important. So I'm going to define mk of G, number of K matchings in G. So K matching is the K tuple of disjoint edges. Okay, so K tuples of disjoint edges. And now here is the theorem. This is by Hillman and Lieb in.
So you care about the ordering?
Yes, yes. I have the edges are labeled and I look at K subsets. So I don't know what you mean by ordering. It's a
Yeah,
subset.
so, yeah.
Ordering is within the matrix.
No, I don't care about that. No. So it's by, I might as well write this. Hellman and Lieb 96. Mk of G square greater or equals than Mk minus 1 of G times Mk plus 1 of G. So beautiful theory. Okay. Very easy to state. So once you look at the result, you look at the original proof. The original proof is linear algebra eigenvalues, not super high. However, if you're a combinatorics, you don't like that. That's not what you want, because because once you subtract, so look at the defectors inequality, by which I mean subtract the right hand side from the left hand side. You don't know what does it count. Now the question is, does it count anything? Well, sort of, in order to figure that out, you need to find a new proof. So here is a proof by Rockefeller. Much later, 96. And
Was the original 66?
no. The original, oh, this is nonsense. The original 70. Of course. Yeah. Yeah, sorry. I don't know where I'm. Okay. So so here is what we want to say. We want to say that Mk of G is the number of elements in a subset of K matchings. So what you want to do is you want to take Mk minus 1 times Mk plus 1 and find an injection of that into Mk times Mk. So if you're into kind of like best case scenario, this is what you want to do. And you can. So here is how it works. And that's where I'm gonna need some colors. So what you do is, again, you go with the best case scenario. What is the ideal thing to happen? Well, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. I don't know. 1, 2, 3, 4, 5, 6, 4. Yeah, how about this?
MK times MK, yeah,
So I'm writing one K with K minus one edges, one with K plus. So there are more of red edges than blue edges. Okay, and when you do that,
There should be two more.
what? Did I miscalculate? 1, 2, 3, 4, 5. Oh yeah, there should be. Yeah, let's arrange it with that blue. Okay, so so when you overlap, there are different scenarios. So what are the components that you get? So you can get cycles. I'm gonna leave them alone. Then you get paths. There are three kinds of paths that you can get. I didn't draw them all. So that there are paths which have equal number of blue and whatever red. Yeah, so even. So I'm gonna leave them alone. I'm gonna have red positive and blue positive. So there are paths where there are going to be more red than blue, and there are going to be paths where there are more blue than red. In this particular picture, there happen to be none. So because the number of red is going to be bigger than blue by 2, so I'm going to say that there are L plus 1 of those and L minus 1 of those. For some L.
Yeah.
Okay, everyone good? So now what we do is we realize that what you can do is you can take any path and recolor red and blue. Just switch the colors. There are 2 L paths, so there are 2 to the L ways of doing that. But we do know that 2L choose L minus 1 is less or equal than 2L choose L from the previous fancy theorem we proved. So there is a way to make an injection of those where we have 2 extra red positive into the one where you have equal number of those with red positive and blue positive. That's it. That gives you the proof. Do you see what I mean? Ask a question if you don't.
Where you do something.
Okay, where I do something. So I'm gonna be recoloring. So I'm gonna be making those 2 pair of matching into those 2 pair of matching. So let me do the visualize thing. This is red. This is red. This is blue. This is blue. All I'm gonna do at the end of the day is I'm gonna take some path and I'm going to recolor them. And but which path? It's not obvious. But because we know that one binomial coefficient is less than another, there is a way to make an injection. And in fact, it's the ones that I already discussed. So I'm going to follow that recipe and find an injection from those pairs into those pairs. And that's going to prove me a theorem. Everyone okay now with this? This is not, I'm not saying anything complicated. Now, everyone sure you're done? Because now I can get a new corollary. So in order for me to
Igor, it's not enough to take the lexicographically first.
don't get ahead of me. Yes, it is enough. From a CS perspective, yes. So I'm just going to put a very big bold square here to indicate that you're done asking questions about this proof. So here is a corollary. And for the corollary, I'm going to write, let's say mu k is going to be equal to sum over all m in mk x to the m. So x to the m is defined as a product of x e in m. So I'm taking a polynomial, basically, think of that as characteristic polynomial corresponding to all k matchings. And now what this proof says is that mu k squared greater or equal than mu k minus 1 times mu k plus 1, where this inequality should be understood not as an inequality for all x's, but that is Hellman and Lieb. You also get an equality, monomial inequality. So when you take this polynomial, subtract that polynomial, that's a negative sum of monomials. You see what I mean? And that doesn't follow from the original linear algebra proof at all. That's why combinatorial proofs are so good. Okay? Because you can't get something for nothing if you get the right proof. Do you see what I mean?
But you said Heyman and Lieb prove it.
So Hellman and Lieb prove it when you understand it. So what does it mean to have an equality between polynomials? You can evaluate polynomials at variables. Then it follows from that. And this is a stronger result. So in fact, it's a sum of polynomials.
My memory is that Hellman and Lieb is just an inductive proof. You just concatenate, you just
Yeah,
string.
so it's if you look
And
inside,
then you can't get what you're claiming out of that by just.
no, you get that.
No, you don't think so?
You don't get that. You get that. I mean, that's my understanding. Yes, that's what I got from the proof. I mean, they didn't look into that. I mean, I'm not saying this is the best result ever. I'm saying this is something that doesn't follow from the usual eigenvalue interlacing kind of proof. Okay, because that you won't be able to understand this. Let me see how much time I spent. Okay, so now I want to tell you what's really going on and what do I mean by everything. So so now I'm going to need to get into a little bit of computational complexity, and the problem with computational complexity is sort of different from what people think it is. So I'm going to write on the bottom here definition. So F is a combinatorial interpretation. Combinatorial interpretation. If F is in sharp P, I'm gonna write that, and then I'm gonna explain what I mean for a while. Okay.
Let's see if you write too low.
I know. Sorry. So, but you know what I just said. I'm gonna need to see it more. I'm not gonna write that here as low here. So the problem is not that sharp P is not known. Sharp P is relatively well known among small circle of people who care about that stuff. The problem is NP. People think they know what NP is, and they really don't. So what do we want at the end? At the end of the day, we want to say. At the end of the day, we want to say something. So let me go back to this inequality. So I wanted this smaller. So suppose, or now let me do it big. So suppose this is B. So this is so A is the size of curve A. B is the size of curve B, and this is curve A. And what so the way combinatorial thinks, the way I described it here, is that you have an injection from A into B. Okay, if you have an injection, then you can say that, well, look, everything that's not in the image of injection is what counts the difference. But now, from a computational point of view, you need certain assumptions. So first of all, you need to say that A is a set of combinatorial objects. What does that mean? What is the set of combinatorial objects?
So do you strongly prefer an inclusion rather than a
Injection.
subtraction in the other direction?
Correct. Yes. There is a reason for that also. So what you want, so first of all, both A and B has to be sets of combinatorial objects. So when you're looking at the object, so in CS language literature, you would see A and B are NP languages. Okay, so when you're looking at the object, so let me write it the most easiest way possible. So it's a set of some kind of objects here. When you're looking at A, you should be able to tell in polynomial time if it belongs to A or not. So A in A can be decided in polynomial time. You see what I mean?
This direction.
Well, I want it for both, yeah.
No, but if you say that you can decide in polynomial time, you mean can convince someone in polynomial. If it's NP,
No. Yes, you can, so you should be able to look at objects and decide in polynomial time.
then it's NP.
Yeah,
So it's a P, it's a language in P, not
sorry, you're right.
Good.
Yeah.
Yeah, good.
Okay, so you want to do it for A, you want to do it for B, but you also want to be able to say, you want to be able to compute phi. Phi should be poly time computable. Because otherwise, this injection doesn't make much sense. So if you, so this procedure that I described here, you can compute it in polynomial time.
Can you elaborate on this? I mean, there's an arbitrary injection that went into the
No, it's not
construction.
arbitrary.
Don't you need to make like a little
I want that one. I want that injection.
But how do you decide which of these paths corresponds to which element of the?
Oh, lexicographic ordering.
Okay.
You pick any ordering that you like, lexicographic works easier. You can just order them all lexicographically, do that. Do according to that rule. And if you do it at the end, the set of objects A in A such that A is not in the image of B, that is a combinatorial interpretation for A minus B. This is as easy as that.
That might not be in P.
No. So what we're saying is that this number is a number of objects. So we no, I think so. I want both phi and phi inverse polynomial time computable. Yeah, so I want to be able to decide if something is in the image. Yeah, sure. These are all easy injections. Yeah, so this is not about cryptography. This is,
Phi and phi inverse to be.
yeah, sure.
So can you illustrate it in this example? Like if I give you something in MK times MK, how do I determine whether it's in the image of MK minus
You have to use the
You do it again. You do it again, and you do it again. You get back something, then you do it forward. You start with that or not. Good question. So those problems, the way I decide them, define them, they didn't come with some parameters. It's not a final thing. So all those problems, the way you should think about it, that this inequality to become interesting, it should depend on a number. It's something sort of interesting. More interesting when it depends on a graph or something more complicated. Then it's polynomial in the input. In the input, whatever graph that is. So here the input is a graph. That graph over there.
And the size is the number of edge.
Say it again?
The size is the number of edge plus vertices.
Yeah.
Yeah.
Yes.
Just basically time to write down the graph. In whichever way you want. After polynomial change, it won't matter. So now.
So it's really important that you are talking about families of inequalities and not.
Correct.
Inequalities. One for every n.
It's not, I really, for n is not really the best thing. It's one for every graph.
Yeah, but in general, I mean, this general set.
So once you phrase it that way, you can then look at other inequalities, and you can ask a question. So here is a de Hackatz inequality. This is from 18. So it says the following: fk of g squared minus fk minus 1 of g, fk plus 1 of g. So, well, that's a greater or equal here. This is for all k, where fk of g is number of k forests in G. Okay.
Use driving force.
K forest means this is subsets of H's without cycles of size k.
But did they expand?
No.
No.
It's a subset of H's. It can be zero empty subset. It's not about subgraphs. It's about subsets of H's.
So can you repeat what you
Yes. So K forest is a subset. K subset of E with without cycles. Okay.
What is
So
K?
what?
Number.
Yeah. And so this is true for every K. And now if you look at that problem is superficially very similar to that problem. Everything looks the same except M is replaced with K. And K disjoint edges are replaced with K tuples of edges without cycles. However, now, so this inequality, Rattenhaller was able to prove using an injective proof, and I gave you stronger result. For that inequality, we don't know. Is there a combinatorial interpretation for the defect, for the difference between two sides? We don't know. But we don't even know if you write similarly. Let me write it this way: phi k of G equal to sum over x to the f, where f is K forest, and x to the f understood in the same meaning as this one. So if you define it that way, sorry, I know I wrote too low. But you know what is the question I'm going to ask now? Is it going to be true? So the question, is it going to be true that phi k squared greater or equal than phi k minus 1 times phi k plus 1?
Polynomial.
Correct. So if you don't put m here, then it follows from the theorem. If you put monomial, we don't know. And I've tried, and by that I mean I asked my graduate student to compute it for lots of small graphs, and he said it seemed to be true. We don't know. We don't know because we don't know that kind of proof. Okay, and
Sorry, what is the M?
what is what?
The M?
Monomial. So when you subtract, is it sum of monomials? Is it non-negative? So it's a stronger notion of positivity between polynomials. And but in reality, I want to make a conjecture that no. So fk squared minus fk minus 1 times fk plus 1 is actually Norton's sharp p. That is not going to be true.
Sorry, what sharp p?
What? No, those are different questions. If that is true, then this, well, under some assumptions, that this might be true. Go ahead.
What sharp p?
So sharp p is what I was talking about here. So I somehow didn't finish, or maybe I did. So sharp p. Let me do a table which will sort of maybe explain this. So I'd rather not define what sharp p carefully, but I'm going to say suppose this is G connected. So this is going to be decision problems, and those are going to be counting problems. If G is connected, that means that it contains at least one spanning tree. So what is the number of spanning trees in G? G contains a perfect matching. What is the number of perfect matchings in G? G contains a Hamiltonian cycle. So those are all decision problems. Here we're going to get number of Hamiltonian cycles in G. So whenever you have a decision problem, you can turn it into a counting problem of counting the number of ways to solve this decision problem. I think I have one more. Oh yeah, I have one more. One more is for algebraic combinatorial is kind of source. So C lambda mu. So if you're deciding whether little coefficient is greater than 0, computing this little Richardson coefficient. And that's because little Richardson coefficient counts the number of certain tableaus. Okay? So it's not super obvious, but those two problems and the last one are actually in P. This is in P complete.
No, the second one is not in, that's permanent.
No, this the decision problem is in P.
The decision problem. So,
Yeah. Decision problem is in P. And that problem is in P for a completely different reason. Here, this can be done polynomial time, and that's it. Oh, actually, well, it's more complicated. This is polynomial time. Those two are Sharp-P complete. This is conjectural to be Sharp-P complete in unary. Unary means you write lambda like number 4 as 1, 1, 1, 1 rather than 1, 0, 0. I don't know how much time I left. So I have a few more minutes.
So for that thing not to be Sharp-P, is it in Sharp-P because you can count you can decide if there's a K-forest and shouldn't that be in Sharp-P?
So I don't know what you're looking at.
That's not in Sharp, your conjecture is not in Sharp-P, right?
I'm conjecture is not in Sharp-P. It's a non-negative integer.
Okay.
It's a negative integer. It's a function. It's a function. It is in. This function is in Sharp-P minus Sharp-P by definition. And it's also non-negative. So it could be in Sharp-P, but it's not. I don't think so. And I don't have time to present all the, I'll continue next time where I'll tell you about all the great things we did in algebraic combinatorics. But let me tell you one result. One result that we proved.
yes.
So so this is a theorem which was published earlier this year. So what is so I'm going to write the theorem and then I'm going to explain it. So the square of the character is not in Sharp-P unless pH equal to sigma 2. So if you don't know what that means, just imagine giant collapse of hopes and dreams and computational complexity. So if you can't imagine that, then this should be a theorem. So now let me explain why is this interesting and what's going on. So this is an irreducible SM character. Pi lambda. Mu is the value of a character on conjugacy class mu. It's been known forever that pi lambda mu is in we would call it gap P, so Sharp-P minus Sharp-P. So it's known, so people in the literature would call it sign combinatorial interpretation. So it's known, so essentially it's known that this is equal to number of certain ring hook tableaus minus number of other ring hook tableaus. Like I'm going to put it 1 and 2. That is known. Now, if you take a square of that, that's a non-negative integer. Okay? Non-negative integers, which is also in gap P, obviously. So non-negative integers tend to have combinatorial interpretation, like here. So we're saying that it's not going to work here. So there is no combinatorial interpretation. And in fact, much stronger result is true that chi lambda of nu equal to 0. This is it. I'm not going to explain what I mean by that. So this is C equal to P complete. Which would, so that means that in this, in fact, you should think of that problem as being equivalent to a problem number of Hamiltonian cycles in graph G equal to, well, that problem is equal to number of Hamiltonian cycles in graph H. So you don't really expect number of Hamiltonians to be able to decide whether this is true. But just because you can decide it, it might still be in the polynomial hierarchy. However, what we prove that it's not. So those problems are incredibly hard, and essentially positivity is PP complete. So it's basically, it's at least, it's definitely pH hard, so harder than the whole polynomial hierarchy. You see what I mean? So and if you go through that and you try to understand what does that mean, if this problem wasn't sharp P, if character square counted something, some set of combinatorial objects, then it would mean through this translation that there would be a witness why number of Hamiltonian cycles in one graph is not equal to number of Hamiltonian cycles in another graph. So if you have two graphs, is there a witness that you can say that those two graphs have different number of Hamiltonian cycles? You don't expect that to happen. That's why character is not unsure. So this is one of the first results that we obtained in this direction, and it's like a proof of concept. I'm not going to give the proof of that, but I'm going to prove some more combinatorial results in this direction. But that's what we're doing. Okay.
This is a very dumb question. Why are the gap classes so much different than the original classes? Why is like sharp B minus sharp B so different from sharp P?
I mean, sharp P minus sharp P may be negative. So what we're saying is that some intersection of gap P with positive function is actually bigger than sharp P. And until we started doing that, there were no natural problems which weren't that. So essentially, just about everything in for combinatorial inequalities, the way they are written with A greater or equal to B, this isn't gap P. The difference isn't gap P. So there is sometimes algebraic, sometimes analytic reason why we have this inequality. And what I want to do is to show that no, there is no combinatorial proof of that. So people have been working for, I don't know, 50, 60 years trying to find the combinatorial proof of that. There are actually papers which admit that that they tried and failed. There is no natural injection. People tried so hard. Stanley wrote in his survey that he doesn't believe this is true at all. He thinks our computers are just too small for this to prove. I don't have an actual quote, but he has it in his survey. So the point is, it's true for a much deeper reason than combinatorial argument.
So essentially, if you had the monomial inequality to the right, then that would imply that it's in the Sharpie?
It depends on what is your, I mean, it's strongly suggested, it wouldn't imply. Because how do you know if monomial is the right monomial? You have to be able to, just on a monomial level, it's not enough.
This wouldn't imply any collapse.
No, but I don't. I think it's unlikely, and just because I think this is not in Sharpie, I cannot prove either one. But this is hard and this is testable at least. So maybe there's a graph on like 300 vertices, which is it's false. Maybe much smaller. I think we tested for up to 8. It's not like we went really far. Testing graphs is hard. I mean, we also tested some random and I saw whatever sort of random-ish graphs on like 20 vertices.
So is sharp P something like you have a set and you have a test in polynomial time which tells that something is in that set and it's the number of elements in some subset. And sharp P means there is a subset of that form where you can test in polynomial time whether it's in that subset. I don't really know what sharp P means. I'm trying to get.
Let's do it again. So if you have a witness, if you have a polynomial time algorithm to decide if the object in your set, then the number of objects is in sharp P. This is much shorter than. I feel I'm taking everybody's time, so thank you all.
More questions?
So you mentioned if you take a random graph, do any of these things actually become much easier to prove? Or is it kind of
I mean, we don't do that because the worst cases are the ones that are hiding. You know, if you take a random graph, deciding if it's recoverable or not is really easy. There are those very few graphs for which recoverability is hard, and they're like tiny proportion of the whole thing. So we don't deal with that. But I understand why you would be asked.
Do you have a specific intuition for why you expect your conjecture to be this polynomial not to be in sharp P, other than that people have tried it
It's
for a long
not.
time?
It's a difference of function. Yeah. So I do, but it's much too vague to answer in public. I think there was another question. Yeah.
Yeah. So I've been asking for a while if constructor constants of forced flag varieties.
I was going to fit that at the end of the talk. I'll start next one with that. So the idea is lecture 2 will be somewhat more algebraic, and lecture 3. So I'll talk about polynomials. Let's put it that way. But I'll start with algebraic combinatorics, and in lecture 3 I'll talk about linear extensions, postsets. It will be much more combinatorial again.
So the case of flag varieties that give a situation where you have one step that's Rosmanian, 2 step, 3 step, that's all sharp P. And then you go to the 4 step, it might not be sharp P and might not be sharp.
Correct. We're working.
So you
As of right now, like that's what I'm not going to tell you the current progress, but we have something coming up soon enough. This is so vague that it's going to be true.
Do you know what the situations where you have?
Do I have intuition? Yes. Do I have a proof? Not yet.
Well, in the I'm redundant. It's a comment. I want to sort of clarify that you started with combinatorial interpretation, and you say I can define it. It has a formal meaning. You know, the problem is inequality has a combinatorial interpretation by definition. If the difference is not
correct,
it is formal.
Correct. That's the only formal thing I can do. This is what's written right over there. Sharp P is the right notion. And it took me over 10 years to basically console myself that this is the right notion. Also, because I wanted to have something much smaller than that, which would be more amenable to combinatorial argument, and it just doesn't work. Sharp P is extremely broad. Basically, just about everything you can think of is in sharp P. So proving that something is not in sharp P is much harder because it's so broad. But that's what we do. That's what we do.
So I had a small comment and a question. Where you put L plus cats, I guess you mean just hog, because that's only for graphs.
No, it's not a chromatic polynomial. It's a characteristic polynomial.
But it still will be implied by hog for graphs only. But I wanted to ask you about the matrix case. Whether
it's so this inequality is true for matroids, correct? And this conjecture would become easy if you put here matroids, but for matroids, you need to talk about the way you input the matroids. So you would have to start with like binary matroid or something like that, and we also do that.
The question is whether you can prove things for matrices that you cannot prove for graphs.
No. It is true that there are some technical lemmas that for matroids are easy. But no. And in fact, you shouldn't expect that I take it back. So in our latest paper about Stanley-Young inequalities, equality conditions, we prove that they're not in Sharpie for general binary matroids, but for graphs, it's a number of spanning trees. You can compute it on polynomial time. So there are results which don't make that much sense for graphs, but for matroids they're much more interesting. But that you can. I didn't want to use the word matroids, but yes, it makes sense. It's just that when you're talking about matroids, you're not sort of thinking of all a collection of independent sets. That's too big. You really have to start with a presentation of a matrix. We typically consider binary, like set of vectors. That's general enough, contains everything you want. And the number of, in contrast with graphs, number of bases for binary matrices just last year was finally proved formally to be Sharpie complete. That was claimed for 30 years, but there was no proof until last year. So.
More questions?
Is there a quantitative version of what you prove, saying if it wouldn't be in Sharpie, but no, maybe it could be in Sharpie time n to the log n or something like that, or does it scale with? You get some consequences from that, or?
For this one, I'm sure you can get something. For other results, I'm going to talk no.
So you will just get a weaker product of the hierarchy, which will be in sigma 2 to time and to the log n.
Yeah, so, right, so from combinatorial point of view, when whatever comes here sort of doesn't matter. So basically something is bad is gonna happen. So one should not try to find the combinatorial interpretation of that, and that's all I care about for the purpose of these lectures. And it's until I basically started pushing it, people give me also when I started pushing it, people didn't believe that this is possible, that you can even formulate this formula. When I started doing it, people gave me an incredibly hard time, basically saying, "Oh, Igor, can't you just prove one more bijection or something? Why do you need to do something destructive? Like, why do you need to have results that are negative? You're killing our dreams." Yeah, okay, so I'm in the business of killing people's dreams. I think that's good for today.